aroma.
Hey, Steve.
Hey, Dr. Javakar, how are you?
Good to see you. We'll let people file in and then, leave it up to you whenever you want to get started.
Sounds good. Yeah, so I guess I can get started.
Sounds good.
Let me share the screen. Well, okay. I'm assuming everyone can see my screen okay.
Yes, we can.
All right, awesome. Dr. Complete gave me the thumbs up, so we're good. I'm going to be doing my grand rounds today on sleep and artificial intelligence. So the purpose of kind of my grand rounds is to kind of give a general and broad idea of what kind of artificial intelligence is out there, what it's being used for, and how we can apply it in kind of our day-to-day practices. So these are my general 4 learning objectives that we'll go through each and every one of them in more detail. So the first one is we'll understand some of the relevant AI terminologies and kind of the different categories of artificial intelligence. So does anyone here have an idea of what the different types or categories of AI? Well, yep. So I didn't know much about AI in general. All I know was ChatGPT can help me with writing a paragraph, and I know that it can help me with creating text or either some content. But there's actually a lot and a variety of artificial intelligence and its uses out there. So these are kind of the 8 main categories of AI. So going from top to bottom, we have reactive machines, limited memory. Some of these are very theoretical and not in practice. So there's the theory of mind. There's weak AI and strong AI, which are kind of one and the same, but and I'll kind of go over this in a little bit detail. There's artificial general AI and kind of linked together with super intelligent AI. And of course, there's the generative types of AI. So from the top, we have reactive machines, which are just very simple AI that does whatever it is programmed to do. It doesn't have the capability of learning from any of these experiences. It only has the program, and it gives a specific set of delivery or output. Limited memory is kind of like the name implies, it has the capability of storing certain memory. So most of the time it has the memory of learning from that specific moment. And it derives the output based on what the program is telling them. Theory of mind is a kind of a theoretical AI where artificial intelligence is able to pick up and is able to understand our mind. So like our mental state, our beliefs, our culture, our intents, and our emotion. We have narrow AI, or known as weak AI. And by all means, it is not weak. And the reason why it is narrow AI is because it is really good at solving one particular problem, and it is designed to perform at a good capacity of that one specific problem set. Then we have general AI, which is similar to weak AI, but it has the ability to apply knowledge in a variety of fields, not only to that specific set of field. Then in combination of both general intelligence and super intelligent AI, these are all just theoretical and hypothetical, where these are the systems of AI that can perform at our human level. And sometimes in hot debate is if super intelligent AI, which is the ability to outperform our ability and in our capacity. And finally, we have generative AI, which is a specific type of AI that is able to create content without any specific type of learning or input. So it can deliver different types of images, texts, music, or any content that you want it to create. So an example of a reactive AI or reactive machine is classically a thermostat, because we give it a set program. It is able to output that set program's parameter based on what you want it to do. So I want the room temperature to be 74 degrees. This thermostat is going to deliver that by telling the whichever system it has to regulate the temperature so that it's 74 degrees. But I guess in this image, 72 degrees. It doesn't have the capability of learning. It can't predict our environment. It can't set our temperature to differences that we feel comfortable. So, which is why it's a reactive or kind of a machine that doesn't have that capability. A limited memory type of artificial intelligence, and it's pretty commonly used in the whole field of self-driving vehicles. So it has a set program, but it is depending, and it's purely dependent on what the input it has, and it stores it into these memories. So, for example, Tesla driving cars, it has the ability to recognize objects. So they're able to differentiate these objects, such as a vehicle from the oncoming traffic, or even in that same lane. It is able to pick up and detect road hazards, road signs, and it's able to pick up pedestrians on the road. And in their program, it is determined to act in a certain way to perform in that driving capability that you want. So I guess for most examples in Tesla driving cars, if you see a car in the oncoming traffic, the role is to not go into that lane. Or if there's a pedestrian on the sidewalk, the role is to not have the car swerve into them and hit them. Narrow AI is actually commonly used in our cell phones. So like facial recognition. So when our lock screen, we can, or I guess I'm presuming everyone has an Apple device, but even Android devices, these are facial recognition patterns that you can detect from a camera, and it locks your phone, and it's programmed specifically to do that task. But you can't ask your unlocking device to, let's say, send a text or do anything outside of that program realm. And finally, we have something called the generative AI. Chat AI is a classic example. They're always constantly updating on their content. It uses an algorithm to create anything that you want. It can output any types of images, or it depends on the certain program. You can have them write something for you, and it just kind of does its best in kind of creating these new content and these new data. So within all of these domains, you have different uses of AI and how it possesses these knowledge. So cryptocurrency mining is actually one of the categories, and it's classified as data mining. There's natural language processing, which is also used in computing, autonomous systems for like self-driving cars, robotics, and things like that. But I like to focus on something called machine learning because it's relevant in the realm of medicine. There are different types of machine learning, and we'll focus on just a few here that I have laid out. But primarily, there's supervised machine learning, and then there's unsupervised machine learning, and then you have the semi-supervised learning parameters that kind of plays into role. So supervised learning is where you have a machine with its own training program, and it has its own algorithm set in such a way that you provide a data set that is labeled. So in this example, you have apples and oranges. You're labeling these data, so apple is apple and orange as orange. And then you have this machine go through these algorithms to decipher, and this machine will be able to distinguish one from the other. And I'm presuming this is fruit category, and it's not going to be color. I don't necessarily agree with orange being a color. But anyways, so when you give the two fruits here labeled under the test data, this machine is able to predict what is this object, and it is able to predict what is the other object. And the main key point here is you have a label data set. So we are giving this machine a label to train on. A part of supervised learning is also a subcategory, which is called deep learning. So there are many layers that we don't see in machine learning, but there are different ways you can manipulate it, and there are different ways that you can tell the machine how to differentiate the one from the other. And this is a general diagram that I kind of provided here, that there are just many types of network that comes into play before the machine can give you that output. Unsupervised learning is different than supervised learning, and it's primarily because you have an unlabeled data here as the input data. you already have a predetermined algorithm or an algorithm that can separate all these different data into their perspective categories, which is kind of what this image is trying to show us here. So then next we can go into what are some of the examples or kind of the artificial intelligence that is being used today. So does anyone know in, I guess, a broad specialty that uses AI or has a general idea of how AI is being used in that realm? I don't think I have a chat box here.
Pathology, radiology, pulmonary too for pulmonary nodules.
Oh, nice. Yeah. So very commonly radiology. So here I have an example of pathology, and this is one of the programs that they use. It is one of the cross-sectional slices from one of the tissue specimen. And here kind of on the left and the bottom left, you have different types of slices. And then you can have this, this machine learning by identifying certain structures and labeling them such in the cell type. Another field that uses it is actually dermatology, and all of these different fields uses an image recognition system, where if you have an image of a skin lesion, it is able to detect with a certain degree of confidence on what it can actually be. So this is kind of the example here. And this is what a dermatoscope looks like integrating this technology. Another example is the use of fundoscopic exam through AI, where it can determine different types of lesions of the eye. Has anyone seen how AI is being used in radiology?
Yeah, there's programs for evaluating large vessel occlusions during stroke pages.
Yeah, exactly. So seeing that you're a very intelligent and expert neurologist, this is one of the dry scan CTs I got as an example from the radiology department at Temple. This is what the AI has outputted for their interpretation. It doesn't give anything specific, it just captures this image and it tells you that there's vessel occlusion. I don't know how it worked and I didn't know why, but in its detail, it has its own set program to kind of look over these layers and identify the difference in the layers with the tissue surrounding it. So it kind of gives you a diagnostic confidence level. And if it's over a set threshold, it labels it as such for the diagnosis. And these are some of the other examples. So kind of like Anusha mentioned with pulmonary nodules, you can also detect PEs. Here's a gaping hemorrhage here you see in the dry scan. And very subtle or not so subtle, depending on how you look at it, with free air in the abdomen. So AI being used in these different specialties are not per se diagnostic. They have been used as a method or as a way of triaging specific needs from each of the studies. So in a routine study in someone with, let's presume a headache, and this is what the AI is capturing for intracranial hemorrhage, this obviously gets triaged to a more emergent study. And the same with an incidental pulmonary embolism in someone with hypercoagulability, then it kind of raises the question of this diagnosis. So it becomes a more higher priority study read for them. So let's get focused on what we can use AI for in the realm of sleep medicine. And to kind of dive in, I've focused a lot on sleep staging. So sleep staging, we go through our training, and then we go through sleep ISR, which compares our scoring with kind of the global average. And here's a slice of my ISR that I did really quickly, and not the flex, but just to show you my score compared to global, so on average. There's a formula that's used to calculate kind of the agreement and disagreement between one of the two scores, and it's called kappa, or Cohen's kappa. So 0 means no agreement, and 1 is ideal, and it is an identical agreement, so complete agreement. In different literatures, the kappa value ranges from 0.63 to 0.76 in different centers, and I have it outlined here. So just to kind of drill the numbers in your head is that the values is typically around 0.63 and 0.76 for human scoring. So going to machine learning and how we're able to input these different sleep stages is that here, number one, you have a typical night of sleep study where a subject goes through a regular night of sleep. We capture the sleep data, and their EEG is essentially processed as a raw data, so the raw EEG data, or it gets computed into something called a EEG multi-taper spectrogram. And I'll kind of go into that in the next slide. But with these two data, we input it into a machine. So we train this machine either supervised, unsupervised, or however many ways it is being used, but primarily they're all supervised learning. And it learns by either machine or by a deep learning network. So an EEG multi-taper spectrogram is basically a plot of frequency from each of the EEG over time. And it plots the density of the frequency from over time. So here we can kind of see that during stage 2, stage 3 sleep, we can kind of get a scatter frequency of around 10, and it's pretty dense on the slower wave here for stage 3, kind of mixed around REM and different kind of densities across this sleep staging. So that is essentially how algorithm is being developed, is where you have these different types of data set, and you have a program that learns by either machine learning or deep learning. And we supervise them because we give them these labeled data sets through the ASM guideline, and in comparison with the sleep ISR. And that is how we develop supervised machine learning for a lot of these algorithms. So what happens next? You either get data that is computed back into a similar spectrogram, you get labeled data, or you get data from these machine learning algorithm with that output of sleep staging just by the EEGs that you give them, or you can have something called a hypodensity graph. So here it is just trying to show you that there are different probabilities for these respective different staging. So from wake, REM, N1 up to N3. And in this hypnogram on top, it is just showing you how it correlates to the probability of how this machine is determining these stages. So kind of from here in the yellow, it is scoring a high probability. So basically 100% that this is wake. And you can kind of see an intermix of different colors with different stages of non-REM. And it is in here, it is picking up pretty good probability of REM sleep, and kind of also on this last REM period. So that is just kind of an example of how it works with respect of hypodensity with their sleep staging characteristics. So this slide, I just wanted to show you that in these two different training sets and testing sets, that they're plotting the kappa values over the amount of training subjects that they have went through. So we can kind of see that both the training and testing kappa values kind of stabilizes around 0.6. And smoothing, which is the graph on the bottom, is when you run the algorithm 5 times in the study, it kind of averages and stabilizes around 0.66. So we don't know how it performed initially. We kind of have these promising data sets where this machine can derive the sleep staging through those 3 probabilities, but we don't really know how it performs. So I have a few studies that kind of highlights how they perform compared to human scores. So here, this is a study done with the Somnolizer. And in this kind of image on the left, you have human scoring, and on the right, you have the auto scoring. And the attention is probably down here for the hypodensity graph. So the probability for human scoring is on the left, and you can kind of see the hypodensity graph being quite similar to the machine scoring hypodensity graph. And in this paper, they're describing the kappa value to be 0.82. So it's pretty darn good. Both of these data are obtained from a recording of 390 PSG data from the Siesta data set. So here's another software that was developed, which is called the Z3 scoring system. This study tested about 2,000 PSG recordings, and these are all taken from a single clinic. These are tested from here, you can see from A to F, and you can kind of see this weird looking table or graph that is black and white and different shades of gray. So basically what this is called is a confusion matrix. Confusion matrix just means it's very confusing to read, and that's my takeaway when I first read it. But it's actually kind of simple. So on kind of the left-hand side on graph A, you can see that the human is scoring different stages, so from wake to REM. And then you have the machine score, which is classifying each stage as wake to REM. And we want to see and compare at which point that they are agreeing completely with each of these epochs or each of these studies. So we're focusing on kind of the leftmost box and kind of going down diagonally to the bottom right box. And these are actually given as a percentage of agreement. And you can kind of see that the agreement here is marginal or can be improved. But on graph A, this confusion matrix is taken from a test of 10 patients. As you go down the alphabet, graph F is where it is taken 1,000 patients.
No worries. That's good.
And they've plotted the Cohen's cap at the 1,000 test subjects to be 0.68.
Yeah. So Anne Marie.
Sorry, hey Fazia, can you unmute your,
messaged
can
me
you
back
mute
and
your
I
mic,
wasn't sure if
please?
it was you guys.
I'll
So
get a hold of her.
I think
It's all good.
I was going to ask her to see this kid the day he was coming back on 18th. I am not in clinic, but maybe she can at least see this kid. And I'll see if I can do it. God, people have called.
So this is a study.
And get transcutaneous CO2 values and everything, because my worry is there's going to be one issue that happens and oh, sorry.
It's all good. This is another study taken from a 1,700 PSG recording, kind of with the same confusion matrices, but here you can see that there are two different sets, which is a training and testing set, and their respective Cohen's kappa score. So it nears around anywhere from a range of 0.7 to 0.8 from this software. And there are many more studies out there that I didn't go in depth here, but there are these different types of software that is actually available publicly. And these are some of the other studies that have shown to have promising validations and with pretty promising kappa values. So far, when I looked in to ASM and the FDA, there's pretty much two that I'm aware of. So Enso Sleep is the first AI-powered kind of a pulse oximetry that is available to detect these respiratory events. There's also something called a Sleep Stage ML by Beacon. But other publicly available softwares that are not FDA approved, and one of them is called U-Sleep. It is actually a website. You can just input data into this database, and then you can kind of see what kind of output it gives you. And this is another example. I believe it's the Sequence SleepNet. Different files, I try to run them. I think my computer is not capable of running them. It has a different software requirement. And I would need to talk to my father for a lot of these program-specific operations. This is the Z3 score again, similar from that study as before. So how about us? I've asked around with Judy on how we can use AI to kind of our advantage. And we do have one in Compumetics, and I'm not entirely clear if this is machine learning or if it's a simple reactive machine that spits out these data based on the parameters that we want to stage each of these epochs in. So this is an example of what it looks like. Sorry, got cut off here, but essentially you can analyze the sleep staging. You can give the different epochs from when it starts to when it ends. This is done on me, so there are no HIPAA violations here. So here, I kind of threw this out there to show you that set one is something that I've created, and it is scored automatically or automated by my by the computer. And then down here, it is a sleep tech that was either in training or is scoring it for practice, and this is done by manual scoring. So overall, this is what the results look like. So from set one, which is the one that I've created for automatic computer scoring, and then this is score set two, which is from the sleep text scoring. So to me, it looks pretty darn close. The concordance is about 73% between machine and in person, and the kappa here is identified as 0.63. So does anyone pick out anything glaringly different between computer scored and human scored?
Slow wave sleep.
Yeah, N3.
Yeah, definitely N3 sleep. So this is kind of an example of what it looks like machine scored. So this is a slice of epoch that I took. The machine is scoring this as stage 2. Where is N3? Oh, yes, that's true. And then this on the bottom is they scored a respiratory event as something that is unsure. And it's actually across all of these scoring. And I was trying to play around with the settings, and I couldn't get the machine to differentiate apneas from hypopneas and centrals from obstructives. And this is to kind of highlight the key differences. So in each of the disagreements between auto scoring and versus human scoring is highlighted in red. And I kind of just picked an example of a slide where the computer scoring is staging this as stage 3, where human is scoring this as stage 2. And here's another example. This is where the machine is scoring this as REM, but the human is scoring this as REM, but the computer is scoring this as stage 1 here. So this is to just kind of highlight everything that was compared across between the two. So there's obvious limitations to using artificial intelligence, and what are some of the major ways, or what's kind of the elephant in the room to how we can improve automatic sleep scoring or sleep staging. And it all stems down to the 2 limitations that I could see. Number one is that in a supervised learning environment, we need a large amount of sample data with labeled sleep scoring and sleep staging for the machine to learn and for the machine to train. And obviously with many studies out there too, is that our training data set is much different than what we see in practice. So patients in our training data sets are typically healthy with 1 or 2 comorbid medical conditions, whereas in the lab we see very different a mix of pathology. Yes, so this kind of gets back to the whole concept of how we can get AI to learn. Because if we're focused on supervised learning and following the guidelines of AASM, what are some of the other ways that we can get a large amount of data set without utilizing or relying on heavily with a lot of our sleep scores or sleep technicians or even us as clinicians? So just revisiting this, we have supervised machine learning, and we briefly touched about unsupervised machine learning. So there's a study that mentions unsupervised with a combination of semi-supervised machine learning. And how semi-supervised machine learning works is that it takes what we have available already with labels, and we mix this with a variety of data sets that are not labeled. And through these kind of two algorithms here and a lot of computational work, the goal is to stage so that both the labeled data set is very similar to the ones that are unlabeled. And the whole premise behind that is stage 1 sleep should look like stage 1 sleep for everyone. REM sleep should follow the REM sleep parameters for everyone as well. And the purpose of this is to kind of make this undistinguished from each other so that you can't tell which one is the training set or which one is the one with the labels and which one does not have the labels. And this is kind of to show you the difference in kappa values with kind of the sequence length or the blocked sequence length. Essentially, it is the program that is designed to analyze these specific epochs and with their epochs length with their computational length. So here we just see that the accuracy and the kappa value increases with the more amount of data that we have. So we can use AI in a variety of applications in the sleep world. So this is just an example of what we can use. And one of them is to detect narcolepsy. And it's kind of on the same lines of sleep staging. Here you have a subject without narcolepsy and a subject with narcolepsy. And this is a sleep study over time. And you have a high probability of densely rapid eye movement stage here in the beginning. You can also apply this concept with detection of respiratory events. So it is calculated in this example of your thoracic circumference or your abdominal movement or respiratory movement, and you plot that against your pulse oximetry with your oxygen levels. Here it is just showing you where sleep technicians score this as a respiratory event, whereas the bottom two is the prediction model based on just different parameters of your respiratory movement or your oxygen desaturations here. There are other things that are coming out as well, and it's been published in literature. One of them is a pressure mapping system where it kind of calculates and it determines your body movement, your respiratory movement. Some of them is also described as a degree of ballistocardiogram, so determining your EKG or your heart rate and your artifact going across these pressure systems to determine apneic events or and things like that. And something we're pretty familiar with here as well is the wearable Oura Ring to kind of determine sleep with its circadian and actigraphy tracking. So this kind of brings to our final objective is to learn and kind of just understand what are some of the things that we're hesitant about in applying artificial intelligence into our day-to-day practices, and kind of what it has the potential for. So these are some of just my general considerations for applying artificial intelligence. So kind of what I got from reading and from understanding how these work is that, like Dr. Kaplish mentioned in the chat as well, is that these databases are not very generalized for the public. Different populations that are being tested in each of these studies do not represent what our real world sleep lab patients look like. And it doesn't even touch upon inpatient sleep studies. Ultimately as well, with Watchpad being one of the, I'd say also consider as an AI technology, is that they still rely on our expertise to stage and score, more so for scoring. There are many events in a PAT event that may not reflect true respiratory events. And with a lot of these AI technologies, it relies a lot on public data. Even if you have encrypted data, there's always a concern for a breach of privacy. And it is becoming more apparent, and even in just this last few months with the pharmaceutical data, infringement, it becomes more skeptical whether or not these AI devices are more beneficial to us than the harm it could potentially bring. And then my last point is, once we rely on AI, we tend to over-rely on them. So it kind of brings a connotation where we may think that we need less sleep techs, we need less clinicians, but it's actually quite the opposite. AI is designed to make things flow better, and it's in some specialties, and actually most specialties, it is relied on to expedite and triage care. And here I just have a general slide on how the future of AI is looking for us, with different technologies evolving for wearable devices. There's different AI technologies being used for different treatment plans and predicting success. And of course, the main thing here is a sleep study analysis or sleep staging analysis.
That was really, really great, Steve. I just had a couple comments. I mean, I know that we can say that it probably won't reduce jobs, but I think we know, especially in medicine and many industries, they definitely are very considerate of cost cutting. So I think that is a lot of motivation for some of this. And if you could have, one tech instead of two, or, for other industries. And I also think it's just kind of interesting to think also, like, with the lawsuits for like ChatGPT and other things of like you already alluded to, these data sets of, it's not even just loss of privacy that, some people like, we have patients release their information, but I think that's really for the video, not necessarily for their EEG and, all aspects of their. So yeah, in order for them to really learn, they're having to get off this, off these data sets of whether people know that or not.
Great job, Steve. Kathy has her hand up. Go ahead, Kathy.
So I would say for the security issue, so obviously at this point now, essentially everything we use for our clinical care is with software, and these can run locally. So you don't have to send these to a cloud. So once a AI-based product is cleared by the FDA, the current FDA mechanism for these is that they're locked. So they're not adaptive machine learning, which kind of like, it's a little bit of a loss because everything would perform better if it continued to adapt once it's in the clinical environment. But like while they're doing the training, it's learning, but then when the FDA clears them, you have to freeze them so they can be deployed on local software. So it's essentially like any software that we would use clinically. We're not taking our patient data and putting it into a cloud, or yet we aren't. So I think, there's always risk there with whatever we do, but I mean, even Epic now is in the cloud and we're using it. So I think it's just an inherent risk of life, like now.
Yeah, that's a great point. And I have seen a variety of image slices being, so for the example of radiology, that they're being hacked into like their system. So for PACS, or I forgot what the other software is, and it's been a hot debate in the realm of radiology, which actually is what restricts their use in some of the centers across. Like when I looked, it was more so across the Northeast.
Steve, I have a question. How do you suggest that, institutions or industry or whoever is, cultivating these data, how do you suggest that they incorporate training data from diverse populations, in terms of multiple ways that you can define diversity, to not have too narrow of a training set?
Yeah, that's a great question. I think it ultimately comes down to having the availability or having these participants go into the study, because ultimately it's hard to find a one size fit all. And for a certain training set or for a certain data to be labeled in their respective disease category, and I mean it takes time. And exactly like what Dr. Goldstein is saying, some of these patients don't have access to care, and we can include these in our training data sets. Or if these patients have, severe comorbidities that eventually there's lead time bias that kicks in, or some of any issues that exclude them from getting these studies done. So I think ultimately it's going to take quite a few years to mature. I think we're getting there, but we have not seen it yet being implemented here, or at least now.
Thanks. I think you saw the comments that were coming through in the chat. Does anyone else have a question or a comment for Steve? Okay, Kathy's got something here. Go ahead, Kathy. Do you want to
Oh, yeah.
share that?
So the other diversity issue, because I think actually like the biggest threat that's unique to AI is the augmentation of care gaps, like you pointed out. So one of the other things, so if you can't have access to care, which is our most vulnerable populations, you won't be included in these data sets where algorithms are trained. And then also because we're still the gold standard, right? And humans have a lot of bias. And so when you have a biased human practicing medicine, labeling data as the gold standard, they're affecting, just kind of their complement of patients. But then when algorithms are trained off those biased humans, it's like amplified. So it really kind of takes those errors and that bias and makes them huge. So it's something I think that people are aware of. We have to be like really, really careful of, that you can't, because otherwise we're in danger of developing a bunch of algorithms that are only suited to a particular group.
Yeah, it's a great point. Anything else? All right, I don't see any other hands up. Steve, fantastic job. Thank you for your grand rounds today.
Great job, Steve.
Thanks, everyone.